this morning's session is Romain Rioux, who will speak on the axiomatization of CP with roots of unity.
So I will present you an axiomatization of the valued field CP with a predicate for the group of unity. So just to start, I want to speak a few words on this kind of structure without valuation. So Zilber show that the field C with the group of unity is omega stable, and to do this, he used a property. So it's more a theorem proved by Mann, affirming that that there is essentially a finite number of solutions of equation implying linear combination of roots of unity. So we will see that when we add valuation, it's very important to understand the valuation of roots of unity. So we have a first result in this direction, proved by John Tate and Joseph Philippe Voloch, claiming that if we take coefficient A1, AN in CP, this set is bounded. So we will see later that, in fact, this set has a maximum, and we will see that this kind of property plays a key role in our axiomatization. So just to have a better understanding of this kind of set, we are going to split you into two different subgroups. So I noted them UP and U over line P. So UP is the group of roots of unity of order a power of P, and U over line P is the group of roots of unity of order prime to P. So I give you basic facts concerning these two groups. Okay, so the residue groups of UP is a trivial one, and the residue group of U over line P is the residue field. Okay, and the value group of the field generated by U over line P is Z. So, in fact, these two groups are definable, and it's easy to see that UP is definable. So, because we can see that UP is the set of these elements. Okay, so that's it's easy, and we can see it's a consequences of this fact by example. And so we will see later that U over line P is also definable. Okay, so now I present you, yes, the plane of my talk. So I first we work with the structures CP with U over line P, and I recall some basic facts, some definition and basic facts about this vector, and after we use it to axiomatize these structures. Okay, and after we see a strong version of the Tate Voloch theorem so when the roots are in U over line P. Okay, and after yes, I will speak about this structure, and first I give a decomposition of linear combination of roots of unity to understand the valuation of this kind of set. Okay, and we will see as a consequences that U over line P is definable, and also we have an improvement of the Tate Voloch theorem. Okay, and after I give the axiomatization of this structure. So just to begin, I recall some basic fact and definition about this vector field. So let K be a perfect field of characteristic P. So there is there exists a unique valued field of characteristic 0 complete with value group Z and residue field K. So we call it the Witz vector field over K, and we note it W of K. So this fact, okay, show that in the Witz vector field there is a unique multiplicative lift of the residue field. Okay, and why we are interested with Witz vector field? It's because the Teichmüller group of the Witz vector field over the algebraic closure of Fp is U over line P. Okay, so yes, so to axiomatize our theory, we use this fact, okay, and it's show that for every fixed collection of elements of Z, there exists an integer such that for any perfect field of characteristic P, the valuation of a linear combination with this fixed coefficient of elements of the Teichmüller group have a valuation, an integer valuation between 0 and this integer, or it's infinite. Okay, so here for us, what we use is this. That's this set is finite, and it's a finite set of integers. So just before giving the axiomatization of Cp with U over line P, in fact, this work is very close to a work of Leuven and Dries, who axiomatize this structure. In fact, his work is more general than that, and the axiomatization of these structures, it's a corollary of its work. So, and us, what we are going to do here, in fact, is axiomatizing these things. And we see that's also the theory of Cp with U over line P. Okay, so I give the language. So LDIV is the classical one-sort language of evaluation field, and I take a predicate symbol, a unary predicate symbol to do the group. So the theory consisting of this set of axioms is complete. So the axiom of algebraic closed field of characteristic 0P, the axiom expressing that J is a multiplicative lift of the residue field, and this schema of axiom that is, in fact, the fact that we see here, expressing this fact. So we can see with that these all three structures are model of T, and by this theorem, yes, we can see, for example, that these two structures are elementary equivalent. Okay, so we will see that this axiom is very strong, and it says that for every model of T, the group generated by the value group generated by the field generated by G aim is always Z. So in fact, that we can see that GM is always the Teichmüller group of some Witz vector field. And we have the following proposition. If M is a Aleph1 saturated model of T, we can take the Witz vector field into M. And so with this proposition, the demonstration of the theorem is very simple. So I just give the idea. So I do it by a back and forth argument, and I take two models of T, M and N prime, who are of cardinality Aleph1 and Aleph1 saturated. And here I have GM. Here I have Gn prime.
Can you explain how you get this product from the axiom?
What?
How do you get this from the axiom, from axiom 3?
Oh, because the axiom 3 implies that the valuation here is always finite and it's always an integer. Okay? It's okay? So here I have my two models, and by this proposition, I have a field here and a field here. So as the residue field of M and the residue field of M prime are isomorphic, we have a field isomorphism between these two fields. I call it F. Okay? And because GM prime is the only lift, the only multiplicative lift of the residue field, we forcibly have F of GM is GM prime. So the field isomorphism respects G. And after, we can easily see that we can extend this field isomorphism when we add an element here, because the value group of this is countable. Okay, so now we use this theorem to prove a strong version of the Tate and Voloch theorem in U over line P. So I recall the Tate and Voloch theorem, and as a corollary, we can see that if we take coefficients in the algebraic closure of QP, this set is finite. So how we can see it? It's only because if we fix coefficient A1, AN in the algebraic closure of QP, the value group of this field is a finite extension of Z. So it's discrete, it's a discrete group, and as this set is bounded by the Tate and Voloch theorem, it has to be finite. So now we can show that this proposition, in fact, when the coefficients are in CP, this set is also finite. So how we can see it? By using this fact. So by the theorem that we proved, we have that CP with U over line P is elementary equivalent to QP alg with U over line P. So the fact that this set is finite implies that there is a minimal distance between two elements of this set. And this is, and we can say it in first order. So in this structure, there is also a finite distance between 2 points of this set. And as the value group of CP is Archimedean, this set is also finite. So now I will speak about this structure, and we will see a decomposition in UP. So for all xi in UP, we have this. The valuation of xi minus 1 is on that form. Okay? So in general, we can't have that these sets are finite. Okay? But I introduce a decomposition to compute the valuation of this set. So the idea is to rewrite some of this kind under this form. So where the alpha are linear combination with integer coefficients of the A and element of U overline P, and where eta 1, eta n are in UP and with all different order. So why we do this decomposition? So the idea, for example, is that the element A1, AN are in QP. The valuation here is always an integer. Okay? And the valuation of the terms of this part for two different terms is always different and always smaller than 1. So when, for example, the coefficient A1, AN are in QP, all the terms here are different valuation. So we can read the valuation of this term here. Okay, so I don't want to explain in general what are exactly the alpha, but I do it in an example to understand how it works, and it's always work on the same way. So, for example, I take, yeah, thank you. A1, Z1, plus A2, Z2, plus A3, Z3, V3. So, first, I rewrite this sum as A1, so with Z1, Z2, Z3 in U. So I rewrite this like this. With the zeta E are in U overline P and the xi E are in UP. So now the idea is to transform these elements. So here we can say that the elements appearing are xi1, xi2, xi3. So we want to replace this element by only one element of maximum order. So here I suppose, for example, that order of xi1 is the same that order of xi2 is bigger, strictly bigger than order on xi3. So the point is I want to transform Xi2 into power of Xi1 in that sum. So here, as the two here are the same order, I can write Xi2 is Xi1 with a power between 0 and p minus 1. So times Xi2 prime with order of Xi2 primes strictly bigger than order of Xi1. So here, for example, I take 2, and to have a very coherent notation, I also pose C3 is, so C3 is C1 0, C3 prime. So now I transform this summand to, so I replace C2 by this one, and I want to force to appear the presence of C1 minus 1 because this is the good things to understand the valuation. So I rewrite them into the form A1 zeta 1 plus A2 zeta 2 C2 prime plus H3 zeta 3 C 3 prime plus A1 zeta 1 C1 minus 1 plus A2 zeta 2 C2 prime C1 square minus 1. So now I replace this using the fact that this it is equal to C1 minus 1 square plus 2 C1 minus 1. And I rewrite the summand into the form A1 zeta 1 plus A2 zeta 2 C2 prime plus A3 zeta 3 C3 prime plus A1 zeta 1 plus 2 A2 zeta 2 OK 3 2 prime facteur de C1 minus 1 plus A2 zeta 2 C2 prime C1 minus 1 square. So now here in this decomposition, if I regard only this part, the roots of unity in UP that appear are 1, C2 prime, C3 prime. Okay? So I have only now 2 roots of unity with in UP, and in the beginning there were 3. So we can continue to the same with the same idea to decompose it into something like that 1, 1 to after to have C3 seconds, and at the end the roots appearing here in UP are only 1. So here, for example, to simplify the calculus, I take xi2 prime equal xi3 prime, and finally we found that is equal to a1 zeta 1 plus a2 zeta 2 plus a3 zeta 3 plus plus a2 zeta 2 plus a3 zeta 3 xi2 prime minus 1 plus a1 zeta 1 plus 2 a1 zeta 1 plus 2 a2 zeta 2 factor to no, it's not that. What's okay, plus okay, plus a1 c'est ça, zeta 1 plus 2 a2 zeta 2 facteur de xi1 minus 1, so plus a2 2a2 zeta 2 facteur de xi2 prime minus 1 xi1 minus 1 plus a2 zeta 2 facteur de xi2 prime minus 1 xi1 minus 1 square. So finally, here all terms have different valuation. Okay, and the point is the coefficient appearing in all sums. So, for example, here there is 2 appearing in. Okay, all the coefficients appearing here depending only on the power appearing here, and always the terms without term like this is the term of the beginning with only roots of unity in U over line P. Okay, so it's the important part. And in fact, before I was saying that if, for example, the coefficients are in QP, all terms have different valuations. But in fact, if the coefficients are in CP, all terms often have a different valuation. So for example, if the maximal order of XE is bigger than something, the valuation of the sums is the minimum of valuation of the terms. So we can use it to see that U over line P is definable in our structure. So what's the point and how we did it? So So to start, I consider this set, the valuation of 1 plus Z1 plus Z2, such as Z1 and Z2 are in U over line P. So by what we see before, this set is a finite set of integers. And so I consider it -1, and I call this R. So A is not empty, okay, and it's a finite set of integers. So what I say, if we consider this, the valuation, if I take Z1 and Z2 in U such that the valuation of 1 plus Z1 plus Z2 is in A, it implies that Z1 and Z2 are in fact in U over line P. So what's we doing this? The point is, if I take Z1 and Z2 and for suppose I suppose that Z1 is not in U over line P, okay, I can consider the sum like this, plus zeta1 xi1 plus zeta2 xi2, where xi1 is different from 1. Okay, so by the rewriting that we do just before, we can write this sum as the form 1 plus zeta1 plus zeta2 plus some terms with, for example, xi1 minus 1 and something else. So the point is, if the valuation is in A, so it's different from 0, and it's applied that this valuation, it's an integer, it's different from 0, and the valuation of one terms after is here, it has to be 0. So the valuation of this sum is the valuation of something with something like that. So terms here, the valuation here are always smaller than 1, so the valuation here cannot be an integer. So it cannot be in A, and so the only possibility to have the valuation in A is that Z1 and Z2 are in U over line P. And so we can define U over line P to be the following set. Is defined like this. So there exists Z2. So no, I give the formula that's defined. So phi de Z is the formula. There exists Z2 such that Z2 appartient U such that Z1 appartient U, and the valuation of 1 plus Z plus Z2 is in A. So we can see this is a definition of U over line P. Okay, so now we can see how we can use this decomposition to prove the following. To prove that if we fix coefficient A1, AN in CP, this set has a maximum. So to do it, it's pretty easy when we have the decomposition. Okay. In fact, we show that there is no strictly increasing sequence in this set. So the point, if I suppose that there is a strictly increasing sequence in this set, so for example, I suppose that the valuation of the sum of AE, Z, E, G for G in N is strictly increasing. So I can rewrite this on the form, the valuation of something like this, zeta ij xi ij, where zeta ij are in U overlying P, and xi ij is in UP. So the point is, by the proposition before, not this one, but this one, we can suppose here that, okay, that's here, we can decompose it to have the valuation of something that alpha E bar and some eta 1 G minus 1 E1 eta n G minus 1 IN. Okay? So by the proposition that we see, we can suppose that the valuation is the minimum valuation of these terms. So as we have a finite number of terms, we can suppose the valuation is only the valuation of the sum terms. So there is a term such that this valuation is the valuation of an alpha E and eta 1 G E1 eta n G minus 1 IN. Okay? So, and where the alpha E, so not alpha E, it's alpha EG, alpha EG. So where the alpha EG is on the form, a sum for beta E AE zeta EG. Okay? So as we see before, the valuation for this number, we have a finite number of possibility. So we can suppose the valuation of this element is always the same. So our valuation, we have the valuation of, we say gamma, plus the valuation of eta 1 minus 1 E1, I1, eta n minus 1 IN. And here, it's easy to see that, oh, sorry, I forgot the G. Okay, and here it's easy to see that we can extract a subsequence such that the valuation of this part is strictly decreasing. So it's a contradiction with the fact that the valuation here is strictly increasing. And so, as a consequence, we can see that this set has always a maximum. Okay. So now I will present the axiomatization of these structures. So I work with the language of a valued group with two predicates for these two subgroups, but it's only because the two subgroups are definable. So it's a choice to have two predicates, but we can only have one. Okay, so the theory consisting of this axiom is complete, and I give all the axioms just before. Just after, sorry. So the axiom of value field of the axiom, okay, of I forgot algebraic closed field of characteristic 0p. Okay, the axiom of the theory of CP U overlying P. The axiom of UP as a valued group, because we can see that if I said big V of x is valuation of x minus 1. Equipped with this valuation, UP is a valued group, and an axiom expressing something of the kind of the theorem of Tate Voloch. But we will see what is exactly just after. Okay, so I give, and in fact, we can see that CPU and the algebraic closure on QP and U are model of T. Okay, so now I give the axiom of UP as a valued group. So the first one expressed that UP is just a multiplicative divisible and a multiplicative divisible group. The second one expressed that the group is closed by extraction of roots of order P. The third one, okay, express that the big valuation is always between 0 and 1. This one expressed that the big valuation of x power p if the successor of the valuation of the big valuation of x, and we have this formula. Okay, this one expressed that between 0 and 1, big V is dense.
Wait, what is big V?
Big V is defined as follows. Okay, and this one express, in other words, we can express if I not Gx to be the set of Y in GP such that big valuation of X is bigger than big valuation of X, and Gx plus is the set of Y in GP such that big valuation of Y is strictly bigger than big valuation of X. So this axiom expresses that Gx quotiented by Gx plus is isomorph to Z quotiented by Pz. Okay, so these are the axiom of UP as a valued group. And how times I have now? So 5 minutes. Okay, so before presenting this axiom, I just want to say a few words about how I do the demonstration of this theorem. Okay, so I do it by a back and forth argument, and the point is so I take two big models of cardinality Aleph1 and Aleph1 saturated and prime. And as above, we start here with G, P, M, and here with G over line P, M prime. And as above, we can have a field isomorphism here between the field Q of G over line PM, and here the field Q of G over line P M prime. Okay, so by the works we do on the by the work of rewriting of a linear combination of roots of unity. If I add here G, P, M, and here G, P, M prime, I can extend here, I can extend the valued field isomorphism here to this field, where this one is Q of G. I not GM the direct product of G overlying PM by G PM. Okay, and here we have Q of GM prime. Okay, and the point is that, as above, we can add elements here to extend this field isomorphism. And the point to see it is that if we add an element, for example, X in an immediate extension of this field, by example, okay, and this is where we use the axiom saying something like the Tate and Voloch theorem, is that if I see the set valuation of X minus K, where K is in here Q of G. So this is not exactly that, but it's the idea, okay? So if I look this set, in fact, this set has a countable cofinality. Why? Because we can express it as a union of n in n, so, and k1 kn in k of this set valuation of X minus k1 g1 minus kn gn, okay, for ge are in G. And so, by the Tate and Voloch theorem, this set always have a maximum. So it's proved that the cofinality of this one is countable. And that's why we can here extend our field isomorphism. So now I present exactly what is this axiom. So I introduce a notation, and for all polynomials P1, Pn in this, and all coefficients in here, I note A of U of P1 of A of Pn of A, this algebraic set. Okay, and we have the following proposition affirming such that if we fix coefficients here, there exist some polynomials here such that for all coefficients and all element X in CP, this set has a maximum if for every element in the roots of unity, there exists an element, so in this set, such that for all elements in this set sufficiently close to X, we have the following equality. The valuation of the polynomial in X is the same as the valuation of the polynomial in Y. And so what are these polynomials? So these polynomials are polynomials that appear in the decomposition of we see before. Okay, so just to finish, I can say that it's possible, and so this axiom is the axiom, are the axiom expressing this proposition. Okay, so to finish, I want to say that it's possible that we can replace this condition by an easy one, but there is work to do to do it. And so here I have the complete theory of this structure, but I don't have quantifier elimination. And so to have quantifier elimination, I think an important step is to understand what sets are definable in U. So for example, we see that U overline P is definable in U. Okay, and I think it's when we add that, probably we can have, when we add this set and a kind of set related to him, probably we can have quantifier elimination. No, we can, yes, we can have quantifier elimination in U, and so after in the base structure.
Any questions? Any questions?
So what do you know about this structure classification theory?
What?
What do you know about the structure in the sense of classification theory? What do you know about the structure in the sense of classification theory?
I know practically nothing.
You don't know if it's NIP.
Probably, but I don't prove it.
What do you guess?
I get, yes, it's probably NIP, but it's not proved now. Yes, but it's not doing for, yes.
Do you prove a quantifier elimination just for the valued groups to axiomatize the?
Yes, in fact, with the demonstration that I give from the completed of the theory, so we can see with argument of this of the same type that we can reduce a formula to a formula without a quantificator, and in a formula where the quantification is only on U. Is that your question or no?
No.
No?
No, it was, yeah. I mean, I ask if for you give the axioms of the valued groups as a valued group, and if this theory has a quantifier elimination in some language, or it is, I mean.
No, because in the value group, so for example, you can't define U over line P. You have to have the field structure to define it. And so it's more complicated than only the structure of valued group.